Okay, so let's continue our afternoon session with Ryan talking about Gapless SPTs.
All right. Thanks. I'd like to thank the organizers for putting together such a stimulating conference. It's been really good. Also, the last 2 weeks of workshop were excellent, and also for giving me the chance to speak about this work. So I'll tell you a bit about Gapless SPTs. We have 3 papers on the subject on kind of different aspects of it. I'll hopefully get to touch on a little bit of each of them, but I'll especially talk about our most recent one on something like boundary, what we want to call boundary deconfined quantum criticality in an SPT transition. And this is really led by Ashwin's student, Saran Prembabu at Harvard. He's a brilliant guy, and he's done a lot of the work on this project. So what are we talking about? SPTs are symmetry protected topological phases, is what it stands for. They're a large but fairly well understood family of topological gapped phases. They include things like topological insulators, Majorana wires, many famous condensed matter systems. We also have a classification theory of them, so we know them pretty well. They're intimately related to 't Hooft anomalies, so field theorists should be interested in them. They're topological phases, which means it's hard to detect that they're there by just looking at local correlation functions. The order parameters tend to be more like line operators, or the most important order parameter really is to study them with a boundary. And at a boundary, you have protected edge modes. Every SPT is associated with a 't Hooft anomaly, and the edge mode has that anomaly. So that's the smoking gun of the SPT phase. In physical systems, there are always, these phases, they require a gap to define them. But in physical systems, there are always gapless modes, like at least there are phonons in crystalline systems. And we wonder whether these gapless modes are going to disorder our edge modes, whether it's going to ruin all of the SPT physics that we like. And in particular, in this talk, we're going to be interested in the stability of the edge mode as you tune the bulk to a critical point, say breaking the symmetry of the problem. And we'll find in some cases these modes are still there, and in some cases they're gone. It's kind of like a anomalous Kondo problem, if you like, this single impurity Kondo problem where you study like boundary CFD with an extra degree of freedom there. We're going to do something like that. We're going to find new stable boundary fixed points that people hadn't considered before. And we're also going to be interested in specifically when the critical point we're tuning to is changing from one SPT to another, because that's kind of interesting because the boundary has to change which anomaly it has. So how does the boundary change its character? It's an interesting question. And if I have time, kind of the stretch goal is to talk about intrinsically gapless SPT phases where we have SPT-like physics, but the edge modes are kind of too anomalous. They don't exist in a local system. So there's physics that topological order that can only happen in a gapless phase. So I'm going to start with a review of gapped SPTs. So these are lattice systems, and this means that the Hilbert space is completely local. So we consider a tensor product of usually finite dimensional Hilbert spaces for each site X in a lattice lambda. And we also want a global symmetry. I'm going to call it G throughout. And it also has to respect this local lattice structure. So what we want for every one of these sites is we want a representation of G, and we want the symmetry to act as just the tensor product of these representations. And then with all that, SPT state is a symmetric state in this Hilbert space that satisfies a special equation, which is that it's related to a trivial state by a local Hamiltonian evolution, where a trivial state means a tensor product state. So one with absolutely no entanglement. So it's just a tensor product over G singlets at every site of the lattice. And then H is just some local Hamiltonian. So when we have a state like this, it's automatically the ground state of a gapped Hamiltonian. the way to see this is to start with the parent Hamiltonian of the trivial state, which you can just take to be as projectors, single site projectors into these X's. And then we just unitarily rotate by this e to the IH. And then we get a Hamiltonian whose ground state is the SPT state. And now we work kind of interchangeably between states and Hamiltonians when we talk about SPTs, because, well, every SPT state is the ground state of a gapped Hamiltonian. And you can also see from this that it's the unique gapped ground state. And if we think about the set of gapped Hamiltonians whose single ground state is our state, that's a convex set. So if we're going to do classification, if we're going to do topology, like we can kind of just choose one of those Hamiltonians, and this choice is totally innocuous. So this equation is really key. And where everything comes in is that, okay, we want the SPT state to be symmetric. And that means we're going to take, we started with a symmetric trivial state. E to the IH can be symmetric, even though H is not. This is kind of a puzzle, but it's true. And we can try to classify GSPT states modulo evolution by actually symmetric Hamiltonians. And the cool thing about quotienting out by these is that now the SPT states actually form a group. So you can take tensor products of lattice Hilbert spaces and tensor products of states. And because we mod it out by symmetric evolution, you can show that there are now inverses. So these states are often called invertible states for this reason. And the strategy for our classification is to construct topological invariants. So in other words, we're going to construct homomorphisms out of this group into some other abelian group, and hopefully find enough of these that we can identify the SPT state completely, and then understand the relations between all their invariants. So the most important invariant comes again from this SPT is e to the IH trivial equation, which is called symmetry fractionalization. So states which come about this way from product states are short range entangled. If you apply the symmetry in a finite region, so if you apply it on the whole space, you just get the state back. But if you apply it on only a region, it's as though you just did something acting on the boundary. So in that sense, it's a short range entangled state like this. The state, deep in where you applied the symmetry doesn't see that you stopped applying it somewhere. So you have like finite Schmidt bases basically. And so in one dimension, it means that it just factorizes into a left operator and a right operator. And we're mostly going to be in one space dimension. And you can actually choose these left and right operators so that you get a linear representation. But the left operator or the right operator on its own is only a projective representation. You can see that the phase factors here are going to cancel out. So if you have a projective representation, you can study this expression, which I called omega. This is, if it's a linear representation, this is always 1, but for a projective representation, it's some phase factor. And up to redefining your symmetry operators by phase factors, this is like a well-defined class in something called group cohomology, which is some discrete set. So the elements, so we associate some group cohomology class to each SPT, and because it's a discrete set, they can't jump unless you're going through a phase transition. So this is a topological invariant of the phase. And it turns out that in one dimension, this is a complete topological invariant. So that's nice. And if you like a field theory view of what's going on, these are gapped states. So we expect that they flow to topological field theories. And this group cohomology class actually gives you the action of this topological field theory, which is a very special kind of topological field theory. It's a gauge theory known as Digraph-Witten theory. So for every element of the group, we have a Hilbert space where we study twisted boundary conditions with that group element. And these correspond to our half-infinite symmetry operators with the decoration at the end. And to get a general partition function, you just have to study a 3-punctured sphere. And wherever you link up these 3 lines, you get a factor of this cocycle. And you can see it's the same cocycle because this is controlling the fusion of these string operators. And in general, we expect this to be a complete invariant. Right? It is the IR limit of the theory, so it better be a complete invariant. But we don't know how to construct it from the SPT phase. So that's an open problem. When we do gapless SPT, we're going to need to combine this with conformal field theory. So now we're going to be studying some 2D conformal field theory with similar pictures. And it's very much what people studied in the old days of CFD, these orbifolds. They had like this discrete torsion factors, which are these omegas, but they were gauging the symmetry. And we're going to be asking different questions because we want it to be a global symmetry. We're going to be looking especially at the edge, which was mostly not studied in the old days. Yeah. Mm-hmm. Yes. Right, so the space is gapped. The statement is that there is a choice of v left, v right, so that all of these equations are true. Now, if you just do symmetry fractionalization, you probably won't get actual projective representation. You'll just get some operators. You can study the charges of those operators. It's also an invariant. It's kind of like knowing the commutators in this group, but you can actually get an incomplete projective, right? Uh-huh. Yeah, so in 2D, you end up getting some kind of string operator at the end of this. Like you apply the symmetry in a region, you get some operator on the boundary, it's line operator, and then you have to think harder about what about this line operator needs to be special. It's not going to be a projective rep, and they're not going to be classified by H2, they're going to be classified by H3. So there's some more complicated thing you need to do, then you reduce to a projective rep. Yes. Yeah, thanks for the question. Yeah. So here is the simplest example. It's called the cluster state. So it's protected by, so first of all, I'm going to study spin systems. So these X and Z are Pauli X and Z matrices on some lattice of spin 1/2. I just write them as capital X and Z, but they're the sigma X and sigma Z, you know. And in this lattice of spin 1/2, the symmetries are going to be the product of X operators on the even and the odd sublattice. And also time reversal, which is just acting by complex conjugation in the spaces. So the SPT state has this funny form, this ZXZ form that you get to see everywhere after a while. And curiously, you can do this as an exercise. The Hamiltonian that gives you this state, actually the antiferromagnetic or the staggered Ising Hamiltonian. So the ground state of HSPT is an SPT state, and it's a very nice state because all of these terms in the Hamiltonian commute with each other. So the ground state is the simultaneous eigenstate of all of them. And in particular, this lets us study a boundary very easily. So we introduce a boundary at 0 just by keeping only the terms which fit in the system. And then we look at how the symmetry acts. And essentially, so suppose we look at how the symmetry on the even sublattice acts. Well, we can use this stabilizer property to great effect. We can eliminate almost all of the operator. We can eliminate the entire operator as it goes into the bulk. And what we're just left with is x0, z1 on the first two sites. And if we do that for the other operator, we get z0. Now, the interesting thing that happened is that these no longer commute. So there's some trickery going on with the other endpoint and how we did these ... dots. But at the end of the day, at this endpoint, we have a projective representation of the symmetry, and there's a twofold degeneracy. Yeah. In this case, it doesn't matter. Yeah, there's this is a translation invariant chain, but yeah, there are ones where it does matter. Yeah. Yeah, this is an open chain. So this is what you get if you just truncate the system, just keep only those terms which fit. Yeah. And you can also say it's projected by time reversal. If we combine our complex conjugation time reversal, which is K, by the diagonal of these two Z2 symmetries, then we get time reversal, which is squaring to -1 at the edge. So you can also think about this as a Cramer's degeneracy, if you like. It's a bit more physical. And from the field theory point of view, there's a couple different partition functions which are interesting in this theory. So we actually can, from the data that I told you, we have a method of writing down this digraph-Witten theory, and it turns out to be this one. It has this formula where A and B are Z2 gauge fields, and W1 is this orientation class. Sigma is just some surface. Now we get to study unorientable surfaces when we have time reversal, because we can use the time reversal to kind of glue it together along we can reverse the direction of time that's allowed. And well, we get a non-trivial partition function. In other words, not just one on the torus and on the Klein bottle. And roughly speaking, these correspond to, of this projective representation, the torus corresponds to the commutator and the Klein bottle corresponds to this other thing. So they're both -1 for this SPT phase, whereas for trivial phase, everything would just be +1. So this is sort of like the beta to infinity limit of these things, if you like. So we're only keeping the ground state. It's like -1 plus like exponentially small in beta. E to minus beta times the gap. So any questions about gapped SPTs before we go on? All right, cool. So now we want to take this SPT and tune it towards a critical point. And what I'm going to do is I'm only going to keep time reversal and this this diagonal symmetry, this product of all the x's, because that was enough. That was enough to have a projective representation on the edge. And we're going to tune a phase diagram that involves all three of these Hamiltonians. So we have the trivial Hamiltonian, the SPT, the cluster Hamiltonian, and just this Ising Hamiltonian, which will lead to spontaneous symmetry breaking of U. And we can draw this phase diagram on a triangle, where in the corners of the triangle, we just have that Hamiltonian, and near that, we're in the phase of that Hamiltonian. And we see some familiar features. You see my cursor? Maybe I can point. Let's have a laser. No, maybe not. Well, on the left, the stick. Okay, good. Yeah. Okay, so on the left, we're just tuning between this Hamiltonian and this Hamiltonian. And so that's the usual transverse field Ising model. As we know, there's this Ising CFT sitting here. But on the other side, something very similar happens. And we know it has to be similar because there's this little h that is actually going to, we have this SPT entangler, this e to the IH guy, that is going to exchange H0 and HSPT. And should have written it, but you'll recall that it was an Ising Hamiltonian. It commutes with this symmetry breaking term. So it just flips this phase diagram over, and actually the center line is symmetric. So we know that there's also an Ising transition here, but I've called it Ising star because we're going to see it's not exactly the same as the Ising model. Well, because of the e to the IH, it has all of the same local correlation functions, but they're going to have different stable boundary conditions, so different BCFTs. And we're going to see that the edge degeneracy of the symmetry breaking phase, of the SPT phase, is going to survive at the critical point. And then it becomes the bulk degeneracy, in fact. Yeah. Yeah, exactly. Yeah, so this is just linear combination of these three terms. Mm-hmm. That's what I'll explain. Yeah, that's sort of the point, is to convince you that even though it has the same local. Yeah. So it has all the same local correlation functions, but boundaries and things are going to be weird because the unitary itself is not like a tensor product of unitaries. If it was, then there would be nothing to say. Yeah, exactly. So we need to have boundary conditions on little h as well. Things are complicated. So one way to see that they're definitely different is to compute one of these partition functions. So the partition function we have available, it's quite easy in this theory, is the Klein bottle partition function. So, but we want to compute it with certain twists to see this SPT term is there. So essentially what we're doing is we're computing the trace of our time reversal, which I've written here as like a reflection symmetry, but it's Euclidean space, so it's the same. in the sector where we've twisted by our unitary symmetry U. So I've drawn that as a blue curve. And so this is a diagram that you glue together and you get a Klein bottle. So you can see it's kind of flipped orientation in the top and the bottom. And then we have this blue curve. So we're computing trace of R in this blue twisted sector. And for the ordinary Ising model, the fun exercise to show that this is the order parameter character. It's just linear in the characters, but you have Q squared. But for Ising star, it's essentially the product of the Ising partition function and the one of this SPT, which is set as -1. So it's minus, and these are non-zero. So they're definitely different CFTs. No, you can just compute. Well, you could compute this on the lattice, but you could compute this on the lattice and see the sign. In fact, what's going on is that, you know, what's the ground state in this twisted sector? Normally, it's the disorder operator of the Ising model, which would just be the product of x's on some half-infinite chain. But here, that's not the primary in the Ising star theory. That's actually a descendant. The primary is this decorated one, which is what you would get by thinking about the symmetry fractionalization in the SPT. And it's T odd because it has this Y, which is imaginary. Good. So these theories differ in the charges of non-local operators. Interacting. So far, I defined it as this model, but if you like, you know, we have this. You can just think of it as a product of this TQFT and this Ising. So we want to study the boundaries as well, and there's a trick to doing this. So yeah, the way I wrote it, it wasn't obvious that you could disentangle the two chains, but you can write it as just an Ising chain with the SPT on top of it, as long as you're careful about the symmetries. And then once you do that, you study a boundary, we can just take our Ising chain to have a free boundary condition and the other chain to have this projective representation. We can forget about everything in the cluster chain except for that projective representation. And then we're left with this kind of Kondo problem where you just have the Ising chain, the free boundary condition, and then you have an extra spin transforming in a projective representation. So the symmetry, if we looked at this diagonal T times U, which I called T tilde, is squares to -1 on this spin. So it has some Kramer's degeneracy, and we want to see if this is stable to now coupling the spin to the Ising, to the CFT modes. So if you like, this is a reducible boundary condition. It doesn't start off life as a Carty state. It starts off as sort of 2 times the free boundary condition, right? Because for either spin up or spin down, you have a free boundary condition. So it's 2 of them. And well, there's one operator we can write that commutes with this, which is Z at this spin, which is going to anti-commute with Y left, but then also we can use the order parameter at the edge, which is going to anti-commute with Ising symmetry. And that's going to be a relevant perturbation because the dimension of sigma at the free boundary is 1/2. And essentially the fate of this boundary condition under this flow is easy to figure out. You just diagonalize Z, and you see according to the eigenvalue of Z, we either have a polarizing field in the up direction or the down direction. So again, it flows to a reducible boundary condition, which is now like the sum of the 2 fixed boundary conditions of the Ising model. So sometimes we call this a spontaneously fixed boundary condition. And what's interesting is that this is actually stable in Ising star. So in Ising, it's unstable. You can think of what we did as basically we just constructed an Ising model with an extra spin, and then we've written the usual ZZ term there, but there's no X term, there's no XL. So we're missing that term. And if this was just if we didn't have this Y in the we're good. If you didn't have that Y in the T action on the boundary, then we could just add this term back. It would be symmetric, and that creates a flow to the free boundary, which is what you expect. Like the Z2 symmetry, the stable boundary condition is the free one, but it's not allowed under T. So this boundary condition, that's the only relevant operator, in fact, that that can do anything to this boundary condition because this theory is so simple. So this is a stable boundary condition of Ising star. If you like, there's somewhat of a bulk boundary correspondence here because the operator mu, this is this boundary condition changing operator. It comes from, it's called mu because it comes from the bulk disorder operator mu, which we also learned was charged. So there's some bulk boundary matching. Now there's going to be degeneracy in this state. But first I have to tell you what degeneracy means for, well, I have to tell you what degeneracy means for the CFT. Essentially what's going to happen is we're going to have two degenerate ground states that, recall our boundary condition is like up plus down. There's 4 possibilities, and these two are degenerate in energy, and then the sort of anti-sense up down and down up boundaries, choices for the boundary conditions are lifted in energy by 1/L. And we consider those just part of the bulk states, whereas the splitting between these is smaller than 1/L. So degeneracy for us in a compact CFT like this one is any splitting between the first couple of states, which is parametrically smaller than the bulk splitting 1/L as we go to large system size. And so we should check that for this boundary condition. And the splitting is going to be generated by the first allowed operator, which he said is going to be irrelevant because it's stable. So we know a priori it's going to be faster than 1/L just by its stability. And well, if we were studying unitary symmetries, we would kind of be done because there was one primary here. We saw it was charged. For unitary symmetries, all the descendants would also be charged. So there would be nothing you can write. And well, that would seem to say that the splitting is just 0, but in actual lattice systems, you'll observe an exponentially small splitting, and there will be some kind of gap that controls that. But for time reversal, things are a bit more interesting because the descendants involve time derivatives, so they have different T charges than the primary. Yes. So the exponential splitting can only happen when there's a gap symmetry, and then the charge gap of that symmetry is setting the correlation length of this decay. But you can say like, yeah, there's part of the symmetry group that's just not acting in the CFT. So it's kind of boring, I think. But actually we were confused. So I'll tell you about what happens here. So the first descendant is T even, and you might think, okay, that's strictly speaking, that is the lightest symmetry allowed operator. But because it's just a time derivative, it doesn't contribute to first order shifts in the spectrum. You can rotate it away in the sense that like mu, unitary rotation by mu is going to generate some, symmetric deformation of your Hamiltonian. You'll get a different eigenstates, but you have the exact same spectrum, so it doesn't cause any splitting. And this keeps happening. So at every stage, so that was the first descendant. Now the third descendant, you might also have an operator, right? But you also have a second descendant, which you can use as a rotation here. And so using that, you can get rid of the third descendant. Sorry, using the third descendant, you get rid of using the second, you get rid of the third descendant. And you just keep going until there's a neutral descendant that you can't get rid of. And it's kind of funny. So the next case also doesn't work. There's 2 and 2. But the first case where you have some perturbation that can possibly do something is already at the 7th level. That's an operator of dimension 1/2 + 7. And the predicted splitting of that from second order perturbation theory is 1/L to the 14. And we actually saw this in numerics. This is exact diagonalization on 14 sites or so. It's amazing. You can see such high power laws in these things. It confused us forever because look how small these numbers are. We thought it must be exponential and that there was a mechanism we were missing. Well, it's algebraic. We were missing this mechanism that leads to a very high power. So that's just kind of like a curiosity in this special model, but I thought it was interesting. Now about this degeneracy, Merman-Wagner theorem forbids discrete symmetry breaking in 0 + 1 dimensions. It's kind of like a simple argument about the free energy. but this edge degeneracy looks kind of like symmetry breaking. So if we study the gapped case, remember we have these symmetry operators which commute with the Hamiltonian. We can think of them as zero mode operators or even as order parameters. They're charged under the symmetry. So like Z1 is charged under the odd symmetry, odd sublattice symmetry. Z0 is charged under the even sublattice symmetry. It's tempting to think about them as order parameters for some spontaneous symmetry breaking. And indeed, there are ground states where, say Z0, like there's a ground state where Z0 is non-zero, and then by the symmetry, you'd say, there's another ground state, so they're related by symmetry breaking. But there's also a choice of ground state that's just as good, where Z0 is zero, such as the eigenstate of the other mode operator, or the other zero mode operator. And in a sense, they're on equal footing. Like usually in spontaneous symmetry breaking, you can form these cat states that are like all spins up plus all spins down, and the 1-point functions vanish. But that state doesn't satisfy cluster decomposition. So you say it's not local. But here, both bases, if you like, satisfy cluster decomposition. So they're on equal footing. It's really quantum degeneracy. Whereas in the CFT, the coupling to the bulk, in a sense, decoheres the edge. It's no longer quantum. There's still a degeneracy though, and it's really symmetry breaking. So remember, in the first step of coupling the spin, we added something like Z0, Z1. So that's gonna ruin one of the zero mode operators, but not the other. So kind of also explains like why we had twofold degeneracy on an interval rather than say fourfold as you have in the SPT phase. So in all local ground states, it turns out that you have a non-zero 1-point function. It's really symmetry breaking. So just to summarize that part, the SPT twist does not modify local correlation functions, but it does modify twisted sectors and the stability of boundary CFTs as a result. We saw degeneracy in the finite size spectrum with a surprising power law. In general, we can prove, I didn't prove it for you, but there's an argument that these twisted CFTs have different boundary states from the untwisted partner. At least one can rule out a certain kind of free boundary condition that we expect exists, that exists in the untwisted case. But we can't prove that there's an edge degeneracy, and it's still open whether the stable boundaries of these twisted CFTs always have some kind of degeneracy associated with them. Next, we'll see an example, though, that's almost like a counterexample. There's a particular boundary phase transition where there's no degeneracy. So that's almost a counterexample. Clearly, one needs more work if we want to even state a bulk boundary correspondence. So, yeah, questions before I move on? Okay, so I'm going to talk about SPT transitions. So we just talked about what happens along this line as we go from the SPT into the symmetry breaking. But of course, we can also tune across the horizontal direction, just adding sums of these two Hamiltonians. Now, it turns out that at the midpoint here, which recall is symmetric under this entangler that swaps the two sides of the phase diagram, these Ising and Ising star lines merge into some C=1 boson. And this C=1 boson is actually totally mundane. There's no boson star CFT, so there's no opportunity to like make a twist of this CFT, basically because if you do so, you just get the same theory back. One way to see that is that e to the IH is actually a symmetry of this point. So kind of twisting by the SPT can absorb it just by some kind of symmetry of the theory. And it actually has an anomaly with the other symmetries, which is how it's going to act as an SPT entangler in the first place. And if you study this twisted torus partition function that I said you should study to see the difference between two of these CFTs, for the compact boson, it's just vanishing. So there's no chance. And indeed, if we study the fate of the edge mode from the SPT side, it's very dependent on the marginal operators here. So I don't remember, I think in this it's at the free fermion point, and I think that the edge just, The edge mode just disappears at the transition, but you could tune the marginal operators in a way that the edge mode would survive and then disappear at some kind of like boundary KT transition as you like tuned the marginal parameter. Cool. So instead, we want to go to a different symmetry class where there will be more SPTs around. We really want to be able to compare two different, in this case, it'll be three different SPT transitions, so that we can say one is non-trivial and the other one is trivial. So Z3 is a good choice, sort of the smallest choice. So now we're going to study a system of Q trits. So they're like spins, but they're dimension 3, and there are things like Pauli matrices, these clock and shift matrices. So I'm still writing as X and Z, but they're no longer Hermitian. So now I have daggers everywhere. And the three models of interest are here. So again, there's like a trivial one, and now the SPT states, there are two SPT states. They look a little more complicated. The boundary of these states is kind of similar to the cluster state. These two Z3s are no longer commuting at the edge, but their commutator is some third root of unity, and it's either 1/3 root of unity for this SPT and the conjugate third root of unity for the other one. That's why there are two of them. Or you could compute this cohomology. Either way, there's three transitions here pairwise, and they're all related by these entanglers that you can map from one to the other. And they're also distinguished by their torus partition functions. Now, unlike the C=1 boson, the partition function we're interested in is non-zero. It does have two degenerate states of different charge though, but only two rather than all three charges appearing and things being zero. And it'll turn out that the trivial to SPT or trivial to SPT prime transitions have only non-degenerate stable boundary conditions, so there's no chance of edge mode, while the kind of one that's distinguished is the one between the two non-trivial SPTs, and that will turn out to have two different symmetry breaking edge phases and a continuous transition between them, which is kind of reminiscent of the deconfined quantum critical point, and that it's an order to order transition. So we're going to study an open chain. There's a choice to make in this model because we no longer have translation invariance. So it actually matters whether we terminate this on an even or an odd site. But we're going to terminate both ends on an odd site just for simplicity and just see what we have. So first we're going to start with just no boundary perturbations. I already wrote the perturbations I'm going to want here, but first we'll just start with the two SPT Hamiltonians. And again, you just keep whatever terms fit in the interval. And there you find that, well, there is one operator, one local operator that we can write that just commutes with this Hamiltonian, which is Z at the first site and Z at the last site. And so this operator, this is like our zero mode operator. It leads to exact threefold degeneracy in the spectrum because it anti-commutes with the symmetry. And you might think that like the cluster state, that it gives you actually nine states, but it's unlike this Kondo problem we studied because it's already coupled by this first ZXZ term. So we're already in this situation where the two ends, the order parameters at the two ends lock together in this kind of like edge symmetry breaking thing. We can also study what happens when B is well, now we want to like get away from this fine-tuned point, and so the operator that's going to be good for us is just x1 and x2n plus 1, because these are anti-commuting with the order parameters. So these are going to disorder. These are going to promote disorder for these edges and give us an interesting phase diagram. And well, we can see that if B is infinite, things are changed. If B is infinite, you can do perturbation theory really easily. You just project out operators which don't commute with X. And so you end up just projecting out the first term here in each one. And well, what have we done? We've just shortened the chain by one site. So now we have a termination on even sites at both ends, or even site at whatever end you took B to infinity. And there, the same argument applies. Now the other Z3 symmetry is spontaneously broken with the order parameter being Z2 this time. And so what we want to do is now analyze the stability away from these fixed points or from these fine-tuned points. And I want to convince you that these are stable phases and that there's also a direct transition between them. So we use some lattice tricks. This anomalous Kondo kind of problem is not really good for us here because, well, we don't have a simple CFT in the bulk to point to. Kind of if you somehow the SPT prime CFT is already the simplest one of the three. But what we can do is we can exploit this product structure. So I don't know if I mentioned out loud, but the bulk critical point is described by this some orbifold of this pot squared CFT. So some central charge 8/5 CFT. And it's not exactly a product because you have to do some orbifolding, but we can exploit this product structure anyway. So there's some non-local mapping of the problem to now a Potts chain just on a single ring where we sum over the flux through the ring. So there's some bond that we get to choose. It doesn't matter where we choose, where we're going to have a phase factor in this hopping. So, and we're going to sum over those. So our Hilbert space has 3 sectors for each of these. And our boundary conditions are just going to become 2 defects in this chain, which turn out to just be modifying the strength of the hopping at this left link or this right link. And well, one thing about this mapping is you have to be a bit careful about the symmetries. So we had Z3 times Z3 symmetry. Now, one symmetry is acting just as the usual, I guess it's product of X tilde here in the Potts chain. And the other one is measuring which of these 3 flux sectors you're in. So we can very easily find our two fine-tuned points in this picture. So B equals 0 is the simplest because the chain is just cut in half. If this B term is 0, we just have a free chain up here, a Potts chain up here with free boundary condition, and Potts chain down here with free boundary conditions. But we have to keep track of this flux sector, and when we have free boundary conditions, those 3 flux sectors are actually degenerate. So that's a 3-fold degenerate state, and you can say the magnetic symmetry is spontaneously broken because that's the thing that measures the flux sector. Likewise, we can also do B equals infinity quite easily. So in perturbation theory, now you just throw out these X tilde terms, and you're going to keep, now this Z dagger Z is going to be like a polarizing field for this free boundary and for this free boundary. So we're going to get some sum over fixed boundary conditions where they're fixed kind of in the same direction here, and you sum over the 3 ways of doing it. And so I write that as AA plus BB plus CC. That describes one of these defects. And that also has 3-fold degeneracy when they both have B equals infinity. That degeneracy now is symmetry breaking for the Z3 symmetry of the Potts chain, because that's permuting these 3 fixed boundary conditions of Potts. The magnetic symmetry, on the other hand, is preserved here, which is, you can see from the flux, like it's going to cause some mismatch between A and A on one side, and then it's going to be like A and B on the other side. So those are lifted in energy, so the magnetic symmetry is, the other Z3 symmetry is preserved in this state. But what this picture really buys us is what is happening at B equals 1, which is going to be the phase transition. So B equals 1 is a trivial defect. It's just a Potts chain all around. We didn't modify the hopping anymore when B is 1. Just a Potts chain with some sum over flux sectors. Well, the sum over flux sectors is kind of interesting, but all of those are all the non-trivial fluxes are lifted in energy over the unit flux. So this has no degeneracy. This point B equals 1. So that's already interesting. And later we're going to see that, yeah, there's a duality, in fact, at this point B equals 1, Kramers-Ronner duality, which acts on the bulk phase diagram of this Potts model. You can think about this as approximately perturbing by the energy operator in a single site and the energy operator at this other site. And so Kramers-Ronner duality is going to invert the sign of this perturbation to leading order. So there's going to be a duality that exchanges the two boundary phases. Good. So I promised you I would analyze the stability of the b equals 0 and the b equals infinity points. Actually, since they're dual, well, they're not exactly dual, but they're very similar to each other. So let me just do b equals 0. So if we look at b equals 0 here, like I said, it's two decoupled free chains with some twist we can kind of forget about. And the most relevant symmetric operator turns out to be b itself, this perturbation, and it's acting as a product of, z is the order parameter field at this boundary, and this z is the order parameter field at this boundary. So it's acting as the product of those two order parameters. That operator at this free boundary has dimension 2/3. There's two of them, it's just a product state. So the dimension is 2 times 2/3, which is irrelevant. So indeed, it is stable to this perturbation, and you can then show that it's stable to all other perturbations. But this is the most relevant one. And this is also the one that gives the splitting. So when we study this on a finite ring, we can look at the energy difference between the ground state and the first excited state. So that'll come from splitting this threefold degeneracy in this magnetic flux sector. And our prediction is that, in second order perturbation theory, you predict it's 1/L to the 2 delta minus 1, where delta is 4/3. That's 1/L to the 5/3. And so we observed this in some DMRG. Basically, we looked at values of b starting close to 0 and then ramping it up a bit. Convergence gets poorer as you go to higher b, so we went to 0.3. Remember, the transition's at 1. And pretty far out on system sizes. This is a log-log plot, so straight lines are 1/L to the slope. And for your eye, this is our prediction, 1/L to the 5/3, and the data matches the prediction very nicely. You can see it's going to 0 faster than 1/L. So it is indeed a degeneracy. And there's going to be 2 degenerate states at this E1 level. So this is a twofer. We got both that the b equals 0 is a stable boundary phase, and also that this threefold degeneracy persists beyond the fine-tune point with some algebraic splitting. So now let's get to the phase transition. So the phase transition, there's a number of ways to look at it. I told you it's kind of it becomes like a trivial defect. So we know there's no degeneracy there. So we know both order parameters should go to 0 at the transition. And we can study how they do that. And we see in numerics that they indeed go to 0 at the special point, b equals 1. Now we use the order parameters z1, which I told you about, and then x1, z2, which I didn't exactly tell you about, but you can think of, in the b equals infinity limit, this x1 was projected to 1, so it was basically z2. So x1, z2 is a good order parameter for the b greater than 1 phase. And this shows all the signs of a continuous transition. You see some power law behavior in the way that the order parameter is vanishing at the critical point, and it also shows this nice duality in that you get the same power law on both sides. And we also see, it's a direct order to order transition. You can see all the points less than 1. This blue order parameter is non-zero. All the points greater than 1. The red order parameter is non-zero. And we can get this power law, of course, from the Potts scaling exponents, because we know that this horizontal direction is tuned by this energy operator at a point. And we know the dimension of that. So in a sense, the fate of the edge modes is that they delocalize at this point. So at b equals 1, like I said, there's no defect. The ring has a translation symmetry, which is a really weird symmetry when you think about what we were doing originally, which was studying this boundary CFT problem, where we break translation, but we kind of want to translate, disentangle the chains and then translate them kind of against each other in a way that is going to be shown here as ordinary translation. But the point is that there's no special point on this ring you might think, okay, where we put this flux is a special point, but you can move that around by unitary operator. So the defect modes have completely delocalized. So at this boundary point, it's like there is no boundary. And it has emergent Virasoro symmetry, which you can see easily here because it's just a single ring, but it's kind of surprising from the boundary point of view. So putting it all together, we can now study what happens to the SPT edge mode as we approach this point, as we approach this transition at various values of the boundary coupling. So in the SPT phases, both order parameters are non-zero. This is kind of like what I said. You have these two zero modes. Now away from the fine-tuned point, you still have a expectation value in both of them. But we have this interesting structure as we approach the transition point, which is that for say, here we plotted mostly the red curve. The blue one looks similar, but to not clutter it, we only included this one slice, but it looks totally dual, just reflected. Let's focus on the red order parameter, x1, z2. So for B above the transition, when we approach from one SPT side into the other, the order parameter, we observe that it dips a little bit, but it remains non-zero at the transition. Whereas as you go closer and closer to the boundary transition, there's a point where below the boundary transition, it has to go to zero there, because that's where that zero mode is delocalized. And see the algebraic behavior there. This is 5/9. At the transition, we have this both order parameters, both SPT order parameters, red and blue. Blue is not drawn, but it's drawn kind of on top of the red one, if you like. It also dips to zero at that point. And so you get this interesting pleated pillow shape of this bulk boundary phase diagram. So to summarize a bit, at this transition between two non-trivial SPTs, we found an interesting boundary phase diagram. There's two ordered phases with boundary symmetry breaking and a direct order-to-order transition between them, which you might call deconfined quantum criticality. You can compare, if you like, to a twist of the same theory, which would just be one of these other SPT transitions. For instance, H0 plus SPT or H0 plus SPT prime. But if you just write down that model, then there's not even a candidate order parameter. You no longer have this Z1 that you would write because X spoils it. And numerically, you observe there's just no degeneracy in this model. And you could figure out what boundary CFTs it has, and none of them have degeneracy either. And so this model kind of surprised us because we didn't expect that. We kind of expected there would always be degeneracy. So we didn't expect this special transition point where there's no degeneracy. And kind of like our bulk boundary correspondence previously would have just been that there's always a degeneracy. Half the modes survive, and you just have to look at the CFT to see what algebraic splitting you have. Now that there's more complicated things, I don't even know how to state the bulk boundary correspondence. So I think it's a nice question to try to figure out. You have this untwisted CFT, and then you have the twisted one, and maybe all of their boundary conditions are somehow the same, but the stability rules are different. And so figuring that out would be very nice. Or maybe we just always have to do this case-by-case analysis. And of course, we wonder if all stable boundaries now are symmetry breaking. So yeah, there are questions about that? So yeah.
How do you construct, this SPT chain to the pods with like two like ladder, post ladder?
Oh, this mapping?
Yeah.
I did not explain it in much detail, but essentially, well, there's this cartoon which Saran came up with, which I really like, which is that you are in this ring where you have the sum over fluxes. And if you like to think in terms of topological defects, you can think of there being like some sum over a defect here and a defect here. And in the world of these defects of the Potts chain, there is this kind of defect n it's a topological defect between the theory and its orbifold. And whenever you have the sum over fluxes, you can write it as a product of that defect and its inverse, and then kind of like wrap them over the entire system. And then that takes you from pot squared to this orbifold of pot squared. And that's kind of what we're doing. On the lattice, it's like a Kramers-Wanier transformation on like the odd sites or something like that. Yeah. So the way of writing the boundary condition is like up plus down. That's this kind of like Carty state formalism. You should not think of that as literally the ground state. Literally the ground state is like up up or down down. Like that's the preferred basis. Those are the ones that satisfy clustering. The one that's like, you know, up up plus down down is a cat state. It doesn't have a factorization of like 2-point correlators. Like the end-to-end correlator is, you can easily see it doesn't factorize. Like you have to yeah, it's a classical superposition, if you like, or it's you know, they're super selection sectors. Yeah, the reason why these are stable, you would think that we can just pick one of these or maybe like disorder them and get a free boundary. But to do that, you need to add some kind of boundary condition changing operator. So you can't just add the order parameter, first of all. That would just pick one of these because that's charged. You might want to add like a boundary condition changing operator that say maps AA to BB or something like that. So that's some disorder operator. And the point of the SPT twist is that's also charged. So there's kind of, these end up being stable. Make sense? Okay. So there's not much time left, but I'll tell you the gist of intrinsically gapless phases. So everything I told you in this talk so far, all of the ingredients from topology came from gapped phases, right? We were just combining SPT phases with CFTs in novel ways. Well, we might want to have something that can only happen in a gapless system. That would be interesting. Well, one thing to look for is to try to look at anomalies. So we're still kind of in the realm of SPT phases, but certainly an anomalous symmetry is going to look very different from how it acts in an SPT. But problem is, like, for studying lattice models, we really want to study on-site symmetries. So when you have these tensor product representations, there's always vanishing Tooft anomaly. But there's a loophole, which is that global anomalies, at least, can emerge in the infrared, so long as they satisfy some anomaly matching condition. So in general, along an RG flow, there's some map from the UV symmetry to the IR symmetry, and the anomalies have to match. And in particular, for this lattice system, the GUV anomaly is going to be trivial. So if we're going to look at the GIR anomaly, we'll call it omega. There's something called pullback, which is just a mathematical map that takes you from infrared anomalies to UV anomalies, or, you know, between any two groups, you have such a map. And basically, we want to be able to write a counter term alpha that trivializes this anomaly, but only when you use the entire UV symmetry. So how is this going to happen? One way it can happen is if the infrared symmetry is a quotient of the UV symmetry by some gapped symmetry. So this can happen when you have a gapped fundamental charges, and in the infrared, like, you only see charge 2 or something like that. And in fact, the simplest solution to these anomaly matching equations is going to come from UV symmetry of Z mod 4 on the lattice, and then we're going to imagine that the odd charge, or the unit charges of Z mod 4 are all gapped. The low energy theory just sees a Z2 symmetry, and that Z2 symmetry can actually act chirally. And it's kind of a nice physical model where this happens. It's in this TJ model. You can think of it, you think of our phase as like a doped antiferromagnet. So you start with some ordered phase, and then when you dope it and you have these holes here, the order is destroyed, and now you have some gapless modes. but those gapless modes retain some of the order. And it turns out that if you study the rotation symmetry, or the fourfold spin rotation symmetry in this model, it squares to fermion parity. In this hole doped phase, the fermions are gapped. So it actually acts just as a Z2 symmetry. And it turns out it acts as anomalous Z2 symmetry. It's kind of weird. It looks chiral in the IR. And we have some field theory understanding of this. It matches our, we can still use our arguments about partition functions and so on to think about this theory. And especially this counter term, we can actually identify in the lattice model the charges of certain long range ordered operators. Match the charges that the counter term tells you that they should have. So yeah, a little summary of that. So basically any gapless theory with a global anomaly can give us an intrinsically gapless SPT. You just have to construct the lattice model. And there have been a few interesting papers recently about this. There's one by Maju and Wang that studied a realization of 2+1D DQCP as intrinsically gapless SPT itself, which is kind of cool. So it has an anomaly, but you can actually realize it with some lattice fermions where there's no anomaly. And for those, you can study the edge, and the edge has kind of impossible boundary states. It has a sort of impossible mixed SU2U1 anomaly. And then more recently, there was this paper by Wen and Potter. They devised many new examples, as well as like a machine for churning out examples of these intrinsically gapless SPTs. And they gave a better explanation of the counter term in terms of some SPT pumps. So what we're still lacking here is a mechanism that doesn't need this gapped charge sector. We have some results in this direction, some ideas, but we're working on it. Cool. So yeah, this is my last slide. What I want you to take away from this is that there's a world of quantum phases and phase transitions beyond symmetry breaking states. Many of the talks in this conference, although very interesting, like most of our phases are symmetry breaking. They exist in stat-mech systems, but SPTs are like, they're different. They're really quantum, and you have to understand extended operators to study them. So I think it's a good challenge, maybe even a challenge for the bootstrap to study 2+1D transitions between SPTs and symmetry breaking states. So there will be something like the Ising model. There'll be like Ising star, not the usual Ising star that people talk about, but the one I talked about, that's like a SPT twist. I think it could be interesting. And of course, theoretical questions like, can we write a bulk boundary correspondence for these gapless SPTs? Are stable boundary conditions always symmetry breaking? So thank you.
Transitions, because isn't the CFT itself it'll just be a standard CFT, right? All local data will be exactly what you expect.
Yeah, all the local data will be exactly what I expect. But I imagine that if you're able to input the local data as well as some data about this twist, which will have to do with defect operators somehow, then you can see a new boundary fixed point. And yeah, maybe the scaling dimensions for that will be different from I'm basically looking for, like we saw, these boundaries like to be symmetry breaking, and maybe that's what happens in these models. So maybe you just end up with I forget if it's the extraordinary or the special boundary, but whichever one orders before the bulk. Maybe you always get that, but I think it actually could be more interesting because what these defect operators look like is they have different kinds of spins where they meet the boundary. But yeah, like to see local boundary operators ultimately.
I guess now you can have global solutions.
Yeah. So now Z2 is on the table because there's a Z2 SPT. So we could just do Ising. It's already interesting.
Any other question? Okay, let's thank Ryan again.